Okay, let's dive into two of the absolute biggest puzzles in all of science. We're talking about a radical new idea that says maybe they aren't separate mysteries at all, but actually two sides of the same cosmic coin. So let's start with the big one. Why are you here? And listen, this isn't a philosophical question, not today anyway. This is a genuine, hardcore physics puzzle. Why do you, or me, or this planet, or anything exist at all? Because, you see, our best understanding of physics, the Standard Model, tells us that the Big Bang should have created equal amounts of matter and antimatter. And when matter and antimatter meet, poof, they annihilate each other in a flash of pure energy. So really, the universe should be this totally empty, boring sea of light. But clearly it isn't. We're here. Something's up. Our very existence is proof that the universe is fundamentally lopsided, that there's some kind of deep asymmetry baked in. And it turns out it's not just one puzzle, but two really profound imbalances that, according to the rules, shouldn't exist. So, on the grandest, most cosmic scale, we have a universe that's all matter, with basically no antimatter in sight. Huge puzzle. Then you zoom way, way down to the building blocks of you and me, and life itself has this bizarre preference for what we call handedness. But what if these aren't two different problems? What if they're actually connected? Well, the clue that might just tie these two massive puzzles together is a surprisingly simple but incredibly deep concept: handedness. The technical term is chirality, and honestly, it's as simple as looking at your own two hands. They're perfect mirror images of each other, right? But try to lay one perfectly on top of the other. You can't. They're different. And it turns out this property isn't just for hands. It shows up in molecules and even fundamental particles. It's a foundational feature of our universe. So what if all this lopsidedness, this chirality, isn't just a cosmic accident? A really speculative but fascinating new framework, it's called Celominisignum, offers a radical explanation. And it proposes a complete shift in how we think about what reality even is. The theory's starting point is a bold one, to say the least. It says, forget matter. Matter isn't the rock-bottom layer of reality. Information is. In this view, matter is just information that's been put into an active kinetic state. And if you start there, everything else gets reframed. Antimatter is no longer some kind of weird anti-substance. It's just potential information. Annihilation isn't destruction, it's just the cancellation of that information. And here's the kicker. Chirality, handedness, stops being just about shape and becomes, well, a kind of protective mechanism. And this is the absolute core claim. The universe's asymmetry, its handedness, isn't a bug. It's a feature. It's like an informational safety lock that creates stability and prevents the entire universe from just canceling itself out of existence. According to this idea, it's the very reason we're here. Okay, that is a properly mind-bending idea, right? But how does something so speculative go from being a cool thought experiment to actual, real science? Well, the answer is simple. You have to try and break it. This brings us to one of the most important ideas in all of science: falsifiability. See, a scientific theory can't just explain stuff we already know. It has to stick its neck out and make bold, new predictions about what we should find, or, maybe even more importantly, what we shouldn't find if the theory is correct. And that's exactly what this theory does. It proposes 3 specific experiments to test the whole idea. Each one is designed to ask a question that has a clear yes or no, pass or fail outcome. This is where the rubber really meets the road. First up, let's zoom into the world of the very, very small. The idea is to basically ask an antiparticle a very direct question. Do you actually care if the thing you're about to hit is left-handed or right-handed? Now, the standard view of physics says, nah, it shouldn't really matter. But Celominisignum, with its whole informational safety lock idea, predicts a clear, measurable difference. The experiment would be to shoot positrons, that's the antimatter version of an electron, at molecules that are perfect mirror images of each other, and see what happens. And right here, this is the kill switch. If, after you do all the careful measurements, there is absolutely no difference in how those positrons react to the left-handed versus the right-handed targets, then the whole informational lock idea is just wrong. The theory fails its first big test. Okay, next up, we scale up from single molecules to the incredibly complex machinery of biology. If chirality isn't just about how things fit together, but about fundamental stability, then what happens when we build life's machinery in a mirror? So scientists can actually do this. They can build mirror image versions of enzymes. It's amazing. Standard chemistry would predict that as long as you mirror everything, the mirror system should work just as well as the natural one. But Celominisignum predicts that one version will be fundamentally less robust. It might break down faster or make more mistakes when you put it under stress. And again, a clean falsifier, a clear line in the sand. If both the natural enzyme and its mirror twin perform identically when things get tough, it means chirality is probably just about geometric shape, not some deeper informational rule for stability. And the theory fails its second test. All right, the final test is the most cosmic of them all. Now, obviously, we can't go to a real black hole, but what we can do is create analogs in the lab, systems that mimic their bizarre behavior right around the event horizon. This tests the whole idea of black holes being like informational reservoirs. This theory suggests black holes don't actually destroy information, they just store its potential. So this test looks for evidence of that. It asks, if you set up the experiment with a left-handed twist and then again with a right-handed twist, does the relation that comes out show any leftover bias? Does it have a memory of the twist it started with? The falsifier here is just as clear. If the emissions coming out are fully explained by the machine's setup and there's no residual memory of that initial handedness, then this part of the theory, the idea of black holes as information repositories, just doesn't hold up. You know, this is the absolute beauty of this whole approach. Because even if all three tests fail miserably and Celominisignum turns out to be completely wrong, we will still have learned something profound. We'll have new, super precise data on antimatter, on mirror life, on black hole analogs. The process of testing a bold idea is never, ever a waste. This whole journey, from a deep cosmic puzzle to a radical new idea to a set of concrete, falsifiable tests, that is the engine of science. That's how we turn the vast, beautiful unknown into the known, one testable idea at a time.